Okay, I'm back just to wrap this up. In the previous videos, we showed that 1 implies 2. We showed that 2 implies 1. We also showed that 1 and 2 together imply 3 and 4. And now we're going to show that 3 and 4 imply 5 and 6. Okay. So here's the proof. It is a combinatorial proof. What we now know is that every line contains n plus 1 points, and every point is on exactly n plus 1 lines. Okay, so suppose F is a model of the finite projective plane axioms. So suppose F is a finite projective plane model, and I want to know how many points there are and how many lines there are. Okay, well, suppose that F has k points in total. This is Gosset's argument. Well, what we know is that every line contains n plus, and we also know already that every line contains n plus 1 points. We know every line has n plus 1 points. Okay, so we can just imagine that there are just tons and tons and tons of points out here. There are k of them in particular. So if I have k points, well, how many lines do I have? So we'll do a kind of combinatorial argument. We'll say, okay, well, every 2 points determines a line. So if I pick these 2 points, there's a line through them. If I pick these 2 points, there's a line through them. If I pick, say, these 2 points, there's a line through them. If I pick these 2 points, there's a line through them. But now I think you see the problem, which is that some lines will go through more than 2 points. In fact, every line has 3 points on them. So a line like this one, is being overcounted, because it's being counted when I choose these 2 points, and it's also being counted when I choose these 2 points and when I choose these 2 points. So the combinatorial argument is we have k choose 2 lines, but this overcounts. Well, by what factor does it overcount? Well, consider a given line and consider how many times that line gets counted. So I'll say we have k plus 2 lines, sort of. So how many times does this line get counted by counting every pair of points? Well, it gets if this line has, by assumption, n plus 1 points, and so each line gets counted. Each line is counted n plus 1 choose 2 times. And so that is the factor by which we've overcounted. If f has k points, by duality, f also has k lines. And so if I have k lines, and each line gets counted n plus 1 choose 2 times, that is going to yield the total number of pairs of points. Another way of saying it, which is how Gosset says it, is that if you just choose every pair of points and then you divide by the factor by which you've overcounted, which is n plus 1 choose 2, then you'll get the true number of lines, which is k. All right, and now you just kind of do a little bit of algebra, and you say, okay, well, k choose 2 is k factorial over k minus 2 factorial times 2. Yeah, times 2. And if you divide that by n plus 1 choose 2, well, that's n plus 1 factorial over n minus 1 factorial times 2. And this is just k. And so things cancel, and you end up with just k times k minus 1 over n plus 1 times n. And yeah, and this is just k. Okay, so the k's cancel, and k minus 1 is n times n plus 1. And so k turns out to be n squared plus n plus 1. So that shows that there are n squared plus n plus 1 points, and there are exactly n squared plus n plus 1 distinct lines too by duality. Okay, cool. I think that explanation was decent. Sure. Yeah. Okay. Okay. Yeah. Finally, we will complete the equivalency by showing that 5 and 6 imply 1 and 2. And this argument is also really cute. So suppose we have n squared plus n plus 1 points. And we also have n squared plus n plus 1 lines. And what we want to do is we want to show that there exists a line with exactly n plus 1 points, and that there exists a point on exactly n plus 1 lines. Okay, well, yeah, okay. So, hold on. So, yeah. Okay, so how can I do this? Well, take a line, and we want to show that there is a line with exactly n plus 1 points. In fact, I can just prove that every line has n plus 1 points, and that will show that there exists one that has it. So take an arbitrary line, and I want to show that this arbitrary line has n plus 1 points on it. Well, suppose it doesn't, or rather, just suppose that instead of having n plus 1 points, suppose it has m plus 1 points instead. Suppose it has m plus 1 points on it. Well, now you just run the entire argument back again. We've already shown that, so take an arbitrary line L. Suppose L has n plus 1 points on it. Well, that means that there exists a line with m plus 1 points. But we already showed that 1 implies 2 and that 2 implies 1. So if there is a line with m plus 1 points, then by running the entire argument back again, I can show that every line must have m plus 1 points. So every line has m plus 1 points on it. Okay, cool. And also, every point is on exactly n plus 1 lines. And we also know that 3 and 4 imply 5 and 6. And so that means, since 3 and 4 imply 5 and 6, by redoing the argument that we just did, what we also now know is that we have m squared plus m plus 1 points and m squared plus m plus 1 lines. And so, but I know by assumption, that's number 5, that there are n squared plus n plus 1 points. So what we know is that n squared plus n plus 1, we have this many points, and we have this many points. And now I claim that if these two quadratics are equal, then that's only true when n equals m. And basically, this is just like an algebra fact. I don't know, you can use like calculus or something. You can consider the function x squared plus x plus 1. And or maybe we could just complete the square or something, right? This is x plus a half squared plus 3/4. And since that's true, I claim that if x is greater than 0, then that means that x is greater than negative a half, which means that x is plus a half is positive, which means that x plus a half squared, is this what I'm trying to do? Well, never mind all this crap. Basically, either using calculus or a little bit of arithmetic, I can show that f is strictly increasing on the interval -1/2 to infinity. And so this function, this quadratic function, is strictly increasing, and therefore it's 1 to 1. And so if these two quadratics are equal, then it must be the case that n equals m. And if n equals m, then I started with this line L, which had m plus 1 point on it. So in fact, this line L must have had n plus 1 point on it. And so I've shown that there exists a line that contains exactly n plus 1 points. All right, so 5 and 6 also imply 1 and 2, and now the proof is complete. That explanation was halfway decent. Perhaps you could get just as good of an explanation by reading Gossett. Anyway, there you go. Cool. Oh, and the final thing to say is that as we've now shown that there's this relationship between the number of points and the number of lines and the number of points on a line, we say f is a model, is a finite projective plane model of order n. If every line has n plus 1 points, every point is on n plus 1 lines, exactly and distinct, and there are n squared plus n plus 1 total points, and n squared plus n plus 1 total lines as well. And so we say that this is a model of order n. Okay, cool. Bye.